Hello everybody, welcome to another IZA DWF arcade video. And yes, it is about the Vectorbeam Italian clones made by MicroHeart. Together with the boards, I've also got a 19 inches CRT vector monitor, which is almost exact copy of the first generation Cinematronics or Vectorbeam design. Actually, I've got one monitor chassis with CRT, deflection yoke and XY deflection transistors, and two video PCBs in unknown conditions, so it would be good if I had a different display option during the troubleshooting of the logic PCBs, and maybe smaller than the 19 inches monitor that takes a lot of space on the bench, like for example my homemade 11 inches vector monitor. The answer is yes. And it's the topic of today's video. This little board that I designed allows to connect a Cinematronics or Vectorbeam logic PCB to any analog XYZ vector monitor compatible with the Atari arcade voltage levels. I've called it the Vectorbeam eliminator. Back in the old days, vector arcade games were quite common. Vectorbeam released its first game, Space Wars, in 1977, then sold its assets to Cinematronics in 1979, and many black and white vector games released by Cinematronics used the same logic PCB and video monitor of the original Space Wars. Their vector generator uses a rather clever analog electronic trick. Basically, the CPU only needs to output an initial X and Y coordinate point and then an X and Y ending point. The ending point output starts a resistor-capacitor exponential charging curve between the 2 points. The CPU now uses a timer to unblank the monitor trays only in a linear portion of the entire charging curve. However, for some reasons, they decided to put the X and Y digital to analog converters and the X and Y RC networks in the monitor PCB, together with the CRT power supply, the deflection amplifiers, and the cathode driver circuit. All that we get from the logic board are 12-bit X and Y values, 2 bits indicating a starting point or a draw ending point, and 2 bits to unblank a trace with 2 brightness levels. A first quick inspection of the video PCBs showed that both of them have a very evident burnt spot under the same power resistor. And a look at the schematic shows that the problem is even worse. Whoever designed this CRT power supply did a particularly bad job. It is, in fact, the worst design I have ever seen of a vector monitor supply. I think I am allowed to make this judgment because I've designed a working CRT power supply for my vector monitor. This is a resonant primary converter with a single oscillator transistor, so in principle this should be a very nice and stable design. However, for some inexplicable reasons, the transistor base is DC coupled to its secondary winding through a diode and an 8-watt resistor. Yes, that's 8 watts, burning the PCB for all the time this has been on. Usually, the oscillator's base is a C-coupled through a capacitor with just a very small DC bias to make it start oscillating at power on. Another not so nice feature of this power supply is the absence of any voltage regulation on the secondary outputs. The oscillator runs off a total of 36 volt fixed supply made with a positive 18 volts regulator and a negative minus 18 volts one. Observe how the high score text jitters and follows the push start brightness changes. This indicates a poor anode supply regulation. And see how jittery are the lines also on the other monitor PCB. In the new revision of their monitors, Cinematronics substituted the whole CRT power supply with this new one made by Keltron, and, to be honest, This is the absolute best design I've ever seen so far, having not only proper regulation of the anode supply, but even a current limit on the oscillator transistor. This circuit is a real beauty. Another issue of these monitors is this one. This picture is way overexposed. But this dot in the middle is not a photo artifact. It is a real spot that appears in the middle of the CRT as some components warm up. In real life, it's very faint, but it can be noticed. Even in this case, both video PCB have the same issue. The spot is an unwanted result for the very peculiar and again inexplicable cathode drive circuit of these monitors. They have used two transistors in a parallel configuration to make different brightness levels, which is as crazy as it can get. At low brightness, only Q3 is turned on. On the high brightness, both Q1 and Q3 turn on. Q2 is always on during the normal monitor operations and is part of the spot killer circuit. When Q1 and Q3 are off and no vectors are being drawn, the XY axis have no deflection voltage, so the electron beam would appear in the center of the CRT if the cathode could source some current to a low voltage rail, but the off collector to base leakage current is exactly what is needed to allow some hundred of nanoamperes of current to flow from the cathode. The 2N5550 transistor has a maximum leakage current of 100 nanoamperes and at 100 volts, which is the exact voltage on this monitor cathode supply, but that is at 25 degrees Celsius. The leakage current can reach 100 microamperes if that transistor could get hot enough. And in this monitor, this leakage current is doubled because we have two transistors in a parallel configuration. If we substituted the 2N5550 with the 2N5551, that spot would become much less visible or not visible at all, since these have much lower leakage current and they are specified at a high voltage too. So there is a very good reason to use only the cascade configuration on cathode drive circuits and use transistors with a very large voltage margin. My 11 inches vector monitor has been designed to work with the original Atari Asteroids game PCB, so it only has 3 analog inputs. Here we can see the original Atari vector monitor input characteristics, so obviously an adapter board must have some digital to analog converters. The Cinematronics monitors use two DAC80 12-bit digital to analog converter ICs. Unfortunately, these ICs are no longer made and I don't want to rely on old stock ICs, so I had to find an alternative to replace them. More precisely, they have used the voltage output version of the DAC80. Basically, it is a resistor ladder switched network digital to analog current converter, plus an internal voltage reference, plus an internal operational amplifier and some resistors to make different configuration of current to voltage converter circuits. With a quick glance at the original circuit and the datasheet tables, we can see that they used the complementary offset binary code output at plus or minus 5 volts levels. After a bit of research, I've decided to use this 12-bit digital to analog converter IC, the LT7541A. In its description, we can read the industry standard magic words. That means that clones of this IC will be in production for a long time. I'm quite sure the original AD7541 is even older than the DAC80. Anyway, it's not so easy to find 12-bit DACs with parallel interface and no data bus control signals in these days, so we must use what we can still buy. Of course, this IC only has the switched resistor ladder, no voltage reference and no internal operational amplifier, but these parts can be added externally. The first issue I've noticed is that this IC works with bipolar offset binary code. not the complementary binary code used by the DAC80. Basically, it means that the output will have the opposite polarity with the same input code. This is not really a showstopper, because we could always swap the two output pins and get the complementary output instead, but this also requires the use of an external feedback resistor for current to voltage conversion, since the internal resistor is directly connected to the out1 pin only. This is not a big problem, but I figured out I'd use a different solution. Since the voltage reference will be external, it can be a negative polarity reference to have the output voltage effectively following a complementary binary offset code. But at this point, I thought to just have two opposite polarity references that I can select with jumpers to easily flip the image on both X and Y axes if needed. Another part of the original circuit that needs to be replicated is the initial point setting and the exponential draw RC network. Here you can see the y-axis part, and the horizontal circuit is identical to this one. The CPU first outputs a binary value to the DAX, then the initial point switch is closed, so the capacitor C101 is charged very quickly to the DAC output voltage. After that, the CPU outputs a final point value to the DAX, and then this other switch is closed, and that connects the DAC output voltage to a resistor-capacitor series network made by R103, R102, and C101. In this way, the voltage on capacitor C101 follows an exponential curve between the initial voltage and the ending voltage. During this time, the CPU uses a timer to unblank the monitor trays and some linear portion of the charging curve. This circuit must be reproduced more or less exactly, but the quad CMOS switch, the LF13331, is no longer made, so again I had to find a similar IC that is still in production. Luckily, this was a much easier job, since the DG412 or even the DG212 are suitable replacement working with the same voltages and compatible with the TTL drive signals. The last part of the adapter will convert the two digital brightness bits to an analog voltage between 0 volts and 5 volts needed to drive the Z input of the analog vector monitor. I think in this case I can come up with a simpler circuit than the original one. Of course, all starts from the digital cable pinout. However, the pinout you can find in the Cinematronics game manual is wrong, so I've just reverse engineered this pinout from the actual monitor PCB. The flat cable going from the logic PCB to the monitor PCB brings also some ground wires, but they are not connected on the monitor PCB. So the only common ground return from the monitor to the logic PCB happens through the power supply common ground. I know the reason behind this choice, but I added a jumper to allow my adapter PCB to have a direct ground return to the logic PCB, in case they are powered by different supplies. The adapter board can accept both a center-tapped AC supply of about 18 to 22 volts or two opposite polarity DC rails of about 18 to 25 volts, thanks to the diode bridge and big smoothing capacitors. Then, two linear regulators provide the plus and minus 15 volts rails needed for the DAC IC and the operational amplifiers. And then, two more linear regulators provide the minus and plus 5 volts for the digital to analog reference voltage. These regulators IC are not intended as precise voltage references, but since the size and offset of the DAC output will be tunable, the actual voltage doesn't really matter. What matters is that the voltage is not drifting as they warm up. The digital to analog converter is more or less identical to the datasheet suggestions, only the reference voltage can be switched between plus 5 volts or minus 5 volts with a jumper. This will be handy if some game have inverted axis, for example. Of course, two identical circuits are needed for X and Y deflection. 2 operational amplifier stages will make the needed current to voltage conversion and the summing amplifier of the output and the reference voltage. This small variable resistor allows to cancel out any residual offset caused by the DAC IC errors and operational amplifier internal voltage imbalances. The init and draw switches are identical to the original ones, except for the actual switch IC. I've used polypropylene low loss and low leakage capacitors, even if it doesn't seem they bothered to use any particularly good capacitor type in the monitors I'm servicing. The final circuits are 2 operational amplifier gain stages, one with a small fixed gain and the other with a small variable gain to allow setting the overall deflection sides. And then we have a circuit in the adapter to convert the 2 active low brightness signals to an analog voltage needed for the Z-axis input. When both signals are at a logic high, both Q1 and Q2 are turned off, so Q3's base is pulled to ground by R27 and the analog output stays at 0 volts. In this case, no trace will be visible on the vector monitor. When one or both digital inputs go low, one or both transistors will conduct, making a variable voltage divider with R25, R26 and R27. This voltage will be then buffered by Q3 that is now polarized to conduction and working as an emitter follower. C19 will smooth any too hard voltage transition if needed. Using KiCad, I've made a quick PCB layout using both SMD and through-hole components. And after a short delay, I've got the real PCBs in the mail. That's nice, isn't it? All the SMD parts are placed on the bottom side. The only IC in an SMD package is the quad CMOS switch, since I have many of them in my spare parts. I've also decided to use SMD resistors, also because I have many of them too. Before installing all the ICs in their sockets, let's check the voltage regulator outputs. -15, +15, -5, and +5, all okay. Then I've checked that I didn't make any bad mistake on the digital connector pinout. I'll first check the outputs with the oscilloscope. This is the X deflection voltage. And this one is the Y deflection. Both of them look reasonable. This is the brightness output and it seems a bit too slow. So let's switch the scope in XY mode now. That's funny. Seems that the deflection outputs cannot be centered. Both axes have way too much offset, and that's weird. It seems that my quick glance at the original circuit was a bit too quick after all. In particular, I've overlooked these 2 resistors. Notice also that they have a different value on the X and Y DAC circuits. So let's try to understand what is their function looking again at the DAC 80 diagram. The added resistor is connected between pin 20 and pin 17, so in practice it goes in series to the 6.3 kΩ resistor that is present internally to the DAC 80 IC. Notice also that the internal reference voltage is 6.3 volts, so if we connect together pin 17 and pin 20, we would obtain a voltage range going from minus 5 volts to plus 5 volts if we used only the 5 kΩ resistor to weight the DAC output on the summing junction, or minus 10 volts to plus 10 volts using the series of two 5 kΩ resistors. This comes from the ratio of the resistor values. When we make the reference voltage resistor higher, we basically translate the whole output range by a certain voltage offset. This is exactly why we observe the offset screen with my circuit that instead assumed a symmetric output voltage range. Of course, the digital signals from the logic board are generated by a program expecting that the DAC have the analog offset inserted by design, and the image appears in the wrong position. The original offset correction I've designed into my DAC circuit has of course a too small range, not even 1 volt, since it was only intended to compensate minor imbalances on the DAC IC and on the operational amplifiers. I can, however, change the reference summing resistor as they did in the original circuit. I'm sure in this case the resistor must have a lower value than the nominal 20 kΩ, because I'm using the opposite polarity output with respect to the original design. In fact, I substituted the resistor with a trimmer. So now I can bring the output signal to rest at the ground level when inactive. Just like this. Then I disconnected the trimmer and measured its value. That would be the new resistor value for this deflection channel. Of course, a similar procedure should be done also for the other axis. At this point, I decided to modify the old design and instead move the offset trimming directly on the reference voltage summing resistor. So, the old small offset trimmer has been removed and the reference voltage now goes straight to the DAC input. Then the summing resistor has been split in a series of a fixed one and a 10 kΩ trimmer. So I cut a few traces and added some wire jumpers to implement the changes on the actual PCB for both the X and Y DAC circuits. Now I'm setting the vertical deflection offset trimmer to center the screen. The horizontal trimmer was already on the right point since I knew the correct total resistance. And we can see the game at tracked mode now. So far so good. As we have seen before, the brightness signal looks a bit too slow. The circuit I've used is very simple, however. The only component that can slow down the output signal is C19 that I've added only fearing that the output could be too fast and produce some visible artifacts. However, the value chosen produces a too slow time constant, so I've decided to just remove this capacitor entirely for the moment. And in fact now the brightness changes look more like square pulses. I think this is much better than before. Now I connected the outputs of the adapter to my 11-inch Spectre monitor for the final tests. So far so good. Let's adjust some settings. Vertical sides, horizontal sides, this is horizontal draw speed, and the vertical speed. So indeed, it looks nice. Let me know what you think. No checking vectors and no central CRT spot here, of course. I've also tested it with the other game PCB. So it's all for this video. I hope it was an interesting circuit to show and I hope that you learned something. If you have any question, use the comment section below. Have a nice time and thank you for watching.